Good day, panelists. Today, we are going to present our thesis entitled Production Control System for Compressed Natural Gas with Web-Based Monitoring Technology and Leak Detection System. Too much reliance on fossil fuels to meet global energy demand also drives current global warming. To lessen dependency and help reduce global emissions from fossil fuels, this study focuses on the production of purified biogas compressed as natural gas that can replace electricity and LPG as an energy source for cooking. The main objective of our research is to develop a production control system for a small-scale biogas facility using the Internet of Things. Here are our specific objectives. Number 1. To produce biogas with a high calorific value greater than 20 megajoule per cubic meter. Number 2. To establish an IoT control, monitoring, and leak detection system. Number 3. To increase the methane composition of biogas to at least 90% of the total gas composition. Number 4. To compress purified biogas into an aluminum cylinder for safer and greater volume of storage. And lastly, to validate performances of digestion and purification using statistical analysis. Here is our conceptual framework. Input to the system is the organic matter needed for anaerobic digestion, which is one of the main processes involved, including purification and compression of biogas. Leak detection is also involved as the study deals with methane gas. After the three main processes, it is expected to produce a purified biogas with composition of at least 90% methane, compressed as natural gas in an aluminum cylinder. The slurry coming out from the digester can be used as fertilizer, and an SMS alert will be sent during methane leakage. There are four main processes involved in this study. Production starts with an anaerobic digestion to produce raw biogas, which then undergoes purification and followed by compression of pure biogas in a cylinder. Leak detection is also included as the study deals with potentially hazardous gases. Shown here are the steps involved in the digestion process. The first step is filling the digesters with pig manure and coconut meat in 85-15 ratio plus 2 liters of coconut water. pH, temperature, pressure will be measured by the sensors as well as getting percentage ppm, concentration of methane, carbon dioxide, and hydrogen present in raw biogas. Collected data will then be displayed to a web server for IoT monitoring. These are the conditions involving pH, temperature, and pressure that are needed to be achieved before permitting gas flow to purification. pH must be in the optimum range of 6.8 to 7.2. Temperature must be within the best range in mesophilic condition, which is 35 to 38 degrees Celsius, and pressure inside the digesters must be greater than 20 psi to overcome the resistance to gas flow. Once ideal conditions of the digestion process are met, valves connecting to the digesters to the purification unit will now open. Raw biogas will first enter the still wood column to hydrogen stripping, then to water scrubber for carbon dioxide removal, and lastly to silica gel column for water vapor removal. After purification, purified biogas will be collected and stored temporarily in a gas holder to prepare for compression. As a pure biogas, its gas composition will be measured again for later comparison to its previous composition. Differential height of gas holder will also be needed to know if there is enough pure biogas ready for compression. These parameters will also be displayed to the web server via IoT monitoring. Gas holder reaching a height of at least 38 cm means there is enough purified biogas ready for compression. This will be checked as well as methane concentration before opening the valves connected to the compressor. Using a compressor, purified biogas containing at least 90% methane will be stored in a refillable aluminum cylinder that can be used for on-site and off-site cooking. Since hazardous gases are present in the site, leak detection system will be provided to minimize the risk. An MQ sensor placed outside the unit will be monitoring potential methane leak. If 1000 ppm of methane leak is detected, all valves connecting every unit of the system will be closed. An SMS alert will also be sent to the user via the GSM module. Figure 7 shows the final setup of a developed production control system for compressed natural gas. The top image shows the digestion, purification, and compression units, meanwhile the bottom images shows the assembly of monitoring and control devices. Successful anaerobic digestion determines the fate of the entire production process proposed in this research. Figure 8 shows the state of the organic mixture inside the digesters before and after successful anaerobic digestion. Presence of foamy bubbles suggests that microbes producing methane have developed. Table 1 presents the pressure, temperature, and pH readings, and Table 2 shows the weight and production rate of biogas in both digesters for 4 weeks. Figure 9 displays the pressure performance and changes in accumulated weight of biogas inside the digesters for 8 weeks. It can be observed that the anaerobic digestion was the best at its third week. inside both digesters were an increase of 8.67 psi from the previous week was calculated for digester 1 and 8.29 for digester 2. However, starting by week 4, the pressure and weight of the biogas started to decrease, which meant that there was little left of organic matter for the bacteria to digest from the initial input slurry. Both temperature and pH values are within the optimal range for anaerobic digestion. Table 3 presents the percentage composition of raw biogas. Table 4 presents the percentage composition of biogas after undergoing purification. Figure 10 displays how much difference there was in biogas after removal of gas impurities. It can be observed that the methane concentration of raw biogas produced in both digesters increase at the end of each week until week 4, and that every methane increases, gas impurities decreases.
On the other hand, the effect of raw biogas purification to the purification units can also be observed. The hydrogen impurity of raw biogas converted the still wood to iron sulfide. Water from the water scrubbing unit turned acidic due to CO2. The color of silica gel also changed from blue to pink after absorbing the moisture of biogas coming from the water scrubbing unit. The following shows the flame test of raw biogas from digesters. Table 5 shows its calorific values, which are in the required range for complete combustion of raw biogas. After purification, purified biogas was collected from the gas holder. The following shows the flame test after purification. The gas holder reached its maximum height every 2 weeks as shown in Table 6, and the biogas collected from it was transferred to the compressor. An aluminum cylinder tank will be used for the storage of purified biogas as natural gas. The following shows how at least 60 psi of purified biogas was compressed, which was found enough to overcome resistance to gas flow. Combustion of purified biogas in CNG form lasted for almost 9 minutes. To prove its application for cooking, it was used to heat 500 ml of water, and the time it took to boil the water was compared to the time it took for the regular butane tank to do the same as shown in Figure 14. Results are shown in Table 7. The purified biogas in CNG form was able to boil 500 ml of water in 5 minutes and 15 seconds. Figure 15 presents a developed web-based software for remote monitoring and control. The top panel is where the users can override the control of valves when needed. Green-colored valves mean that the valve is opened. Red if closed. Bottom left panel are the trends and settings, and when clicked, the top panel changes the graphical presentation of the sensor data. Both digesters were operated in similar environment, and so the parameters that set conditions inside digesters to produce enough biogas must show no significant difference. Table 8 shows the T-stat and T-critical value between parameters measured from digesters. The null hypothesis is no significant difference between the parameters measured inside digesters 1 and 2. All T-statistics are less than its corresponding T-critical value, hence null hypothesis is not rejected, and the difference in performance of both digesters measured by its parameter is not significant. To prove that the difference in gas concentration before and after purification is significant, third t-test was performed. Results are shown in Table 9. The null hypothesis is there is no significant difference on gas concentrations before and after purification. Absolute values of all t-statistics are greater than its corresponding t-critical value. Therefore, null hypothesis is rejected, and the difference in gas concentration of biogas before and after purification is significant. The researchers have established the setup of a control system for the production of compressed natural gas derived from biogas. Pretreatment and increased volume of organic matter as well as the addition of bioballs lead to a successful and improved anaerobic purification using steel wool, water, and silica gel successfully increased methane concentration and calorific value of biogas to a maximum of 92.84% and 37.59 megajoules per cubic meter, which makes the product equivalent to natural gas. At least 60 psi of purified biogas was compressed into an aluminum cylinder as CNG and was used to heat 500 ml of water, where it took 5 minutes and 15 seconds to bring the water to boil, proving its cooking capability. The developed web-based software made remote monitoring and control of the system possible with the addition of solenoid valves, enabling faster response time, and GSM module that allowed the system to send SMS alerts during external gas leakage. Lastly, t-tests have validated the effectivity of digestion and purification processes.